Welcome back to the transformer protection topic. I'm Pratap Mysore. This is part two of the lecture on the transformer protection, especially differential protection, covered in the power system protection lecture series. We looked at the basic configuration of the transformer, and also we looked at how the CTs are selected on based on the CT ratios, and how sometimes the CTs have to be connected also based on to cover for the phase angle relationship. And we did cover some of the basic concepts of differential protections in the bus relay bus protection topics. So it would be nice for you to look at it and then continue with the transformer. And this is the part two of that. We looked at the harmonic blocking relay, which is trying to differentiate between an inrush and the fault condition. And by looking at the percentage of harmonic, second harmonic in the operating current. If it exceeds some value, then it determines that it is an inrush and blocks the relay from operating, even though the slope, which is just a ratio of a percentage of the restraint current, if the operating current is greater than the restraint percentage of restraint current, even though that is satisfied, if the harmonic content is higher than a preset value, then it blocks the relay, deciding that it is just an inrush and not a fault. In the harmonic restraint relay, unlike harmonic blocking, it just changes, modifies the minimum pickup of the operating current by adding additional restraint based on the harmonic content of in the operating current. So it is a number here from 0 to 10 or whatever based on the manufacturers. So it multiplies the harmonic current, actual harmonic current, by that value and adds on to the restraining relay. So it not only looks at the restraining current, but it looks at the harmonic current also and changes the slope. So if you plot this, it looks as if the operating current is keep on just increasing based on the harmonic content. Now let's look at the phase angle relationship, how it is taken care of in the transformer protection. Let's look for take for an example a delta Wye transformer, and then it is a three-core, three-limb core transformer, and each limb here they have two windings. One is the primary winding, and then one is the secondary winding. And then this is for the A phase, B phase, and C phase. And the way they are connected, the high side the winding is on one, each limb is connected between two phases. For example, this is connected between A phase and C phase, and then the B phase one is connected between B and A, and C phase is connected between C and B. And then the low side, they have formed a common neutral by shorting the non-polarity side and bringing out to a terminal called X0 bushing, that is a neutral. And then you have got A phase, B phase, and C phase. So if you look at it here, the winding A to C is on the A phase, and this is sharing the same flux as A to neutral winding on the low side. So these two are in phase. Essentially, it is a flux interaction. So these two are in phase. And then B phase is on the low side is in phase with AB, and C phase is in phase with C2B here. So if you create a Y inside this delta, and then the Y A to neutral, which is a neutral, virtual neutral here. So A to neutral voltage is in a 12 o'clock position, and then that is, and whereas the low side A to neutral is lagging this by 30 degrees. So this is why we call this as there is a phase relay shift between the A phase voltage on the high side to the A phase voltage on the low side. So now if you look at this, the low side voltage lags the high side voltage by 30 degrees. We assume the counterclockwise direction is positive, so you get the delta A phase first, and then the YY side as a second. So it's same thing how they are connected. I have shown this in the second slide here. And then as we look at it, the Y side voltage lags the high side voltage by 30 degrees, as I explained to you. If you look at the current coming into the transformer is taken as positive, current going out to the transformer is taken as negative. So if it is a resistive load on the low side, the current coming in on the high side is resistive, is in phase with the A phase voltage. So A phase current and A phase voltage are in phase, and then the low side, A phase current is going out to the transformer, it is negative, so it is 180 degrees out of phase with the A phase voltage on the low side. So if you look at these two, that there is a difference between these two. This is 210 degrees, and then and then this current, the low side current, lags the high side current by 210 degrees. If you look at the transformer currents and look internally, you have turns ratios of A to neutral and A to B windings determine the ratio of the currents. So this is essentially the low side current divided by K, and then this winding current on the B to A will have IB by K and IC by K, where K is a transformer turns ratio, and the current that is coming out of the bushing is nothing but IA minus current that is coming in here is IA minus IB divided by K. So the relationship between the phase currents of the transformer on the high side and the low side are determined by these equations given here. And then as per ANSI, the standard transformer, the low voltage winding will always lag the high voltage winding by 30 degrees. It has been standardized in the United States by the American national standards. Uh, Whereas in Europe, each country has its own rating. So the low side can be lagging the high side in the opposite direction. Instead of 30 degrees, it will be about not 210 degrees. That and or it could be if the low side is leading the high side, it could be lagging either leading the high side or lagging the high side by 30 degrees or 150 degrees. So there are various combinations which we will go through at the end of this when we talk about vector groups in the transformer, the way IEC, International Electrotechnical Commission, determines it, which is a standard all around the world outside United States. So if you look at a differential relay, I operate and I restraint you have got a minimum pickup that accounts for any errors in the CTs, and then then the relay is allowed to operate if the operating current exceeds the restraint current by a percentage slope, as we call it is a ratio of these two. Then we select it based on the type of the relay. If in microprocessor based relays you can set it to any value, whereas in electromechanical relays there were only fixed, there were limitations on how much you want on the slope. Okay. Then your CT connections, if you look at it, I went back and we know the relationship between the high side A phase current and the low side A phase current. High side A phase current was IA minus IB divided by the turns ratio. So we tried, if they are like that, then they are in phase essentially. That is what it is. So if you look at it here, we connected the Y side, the delta side CT is in Y on the high side, and then the low side in delta. So what we are seeing here is the IA current which is coming in here will be IA minus IB on the low side. These two currents will be 180 degrees out of phase. You can go through and then look at it, how it is possible, and then you find that these two currents will be out 180 degrees out of phase, and they select the CT ratios in such a way the magnitudes are close to each other. Okay. CT connections, delta Wye transformers. If we recall now, just summarize this. Delta side CTs are connected in Y, and then Y side CTs are connected in delta, similar to the main winding, but it is in opposite directions. A delta Wye transformer has a Y delta CT connections on each side of this. Currents in the relay are in phase or out of phase during faults or during normal operating conditions. And during normal operating conditions, current is entering the transformer and current is leaving the transformer on the low side. It's entering on the high side and leaving on the low side. So they are 180 degrees out of phase. With the phase angle correction, the relay also sees, They are seeing 180 degrees out of phase, even though the main currents may be shifted by 30 degrees, plus minus 30 degrees on around 180 degrees. In some cases, in an ungrounded system, you want to make the system grounded so that if for single line ground fault, the voltage rise on the other healthy phases is kept to less than about 25%. So if you do that, if you have that grounding bank, it for phase to ground faults, it provides a current on the via delta side, whereas that is not accounted by on the high side. So what we do is we try to put a zero sequence trap. This is only of historical significance for you. You have to go through the electromechanical catalogs to look at it, whereas in microprocessor based relays we take care of this by not considering the zero sequence current for calculations wherever there is a zero sequence source. So this essentially, this table essentially summarizes. If it is a Y delta transformer, we are using delta and Y, and then you can ignore the zero sequence trap because the Y side is connected in delta. It is IA minus IB, takes care of the zero sequence. And if it is a delta Y, and then same way we are connecting it CTs and Y on the delta side and then delta on the Y side. So there is no zero sequence current coming into the relay anytime. If it is a YY, if you connect the CTs in Y, then you have to account for the zero sequence. So the best way to do that is to connect both of them in delta, and then you don't have to worry about this. Okay, so if it is a YY transformer, they are connected in delta. CTs are always connected in delta, or an auto transformer or a YY transformer, to avoid the misoperation due to zero sequence during ground faults. And this is with the 3-winding transformer. The delta side is connected as Y to account for the phase shift. So in the modern relays, all these complexities are not there. You have to tell the relay how the transformer is built, and then what is the vectorial relationship between the high side and the low side, and then the relay automatically takes care of this phase shift and magnitude corrections. The concept of how you define a transformer also has been changed, is different in European world. Suppose in the ANSI, we always say delta and Y step-down transformer, low side lacks the high side. That is a standard. But they don't tell on the nameplate how their vector relationship is there, other than providing you a picture. In the IEC, they always refer it with the designation as dy, n, and 1. And this is for a delta Y transformer. The capital letter here designates the high voltage winding. The delta side is the high voltage winding, and so it is referred to as capital Y, and it is always capital D here, and it is always taken as the reference. And then the smaller lower voltage winding is a Y winding, so it is designated with a small letter Y here, and N just tells you whether that neutral is available or not, dy1 or dyn1, and one number designates that the low side is lagging the high side by 30 degrees. Okay, this is a very common configuration. Now ANSI also, American National Standards also designate their winding phase relationship with the same numbers. They have harmonized the standards with IEC. So here you have this position as 0 or 12, 12 o'clock of a clock, and you have got 1. If you say the winding has got 1 and it is lagging the reference winding by 30 degrees, if it is 11, it is leading the reference winding by 30 degrees. So if it is the polarity of this is reversed on the low side, the 11 becomes 5, so it is lagging the reference winding by 150 degrees. And then if it is YY0, that is a 2-winding transformers, then it is the same as this. There is no phase shift. If the polarity is reversed, it becomes YY6. Similarly, for example, Y1, we said that if you change the polarities of the windings, then it can become Y7. That means it is lagging the reference winding by 210 degrees. If you go to Europe, they have got all combinations here. So the IEC allows them to tell exactly how the windings are configured. Okay. And we have a special group called vector group, which we'll decide, I will explain later, that takes care of ignoring the zero sequence quantities. So similarly, if a low side leads the high side, dy 11, Wye transformer is shown like this, 3 winding transformers with the delta lagging the Y winding is shown as 1 here. So these are simple explanations. You please go through this, then you understand it very well. The high voltage winding is always a capital letter, the low voltage winding is always a small letter, and the number tells you the phase relationship between the high voltage and the low voltage winding under consideration. If it is a Y, it is a small y. If it is delta, it is a small d on the low voltage, and 0 or 1 tells you whether it is in phase or it is lagging by 30 degrees, as in the case of delta. So in the case of modern relays, we always connect CTs in Y. It is a lot easier. But if you have an existing electromechanical relay that is being replaced by a microprocessor based relay, you don't want to go back and rewire this. Sometimes they keep the same. So you have to be very sure what you are trying to, how you set the microprocessor based relay, like, how the CTs are connected. So yeah, in most of the cases, it is connected as Y irrespective of the transformer winding. Relay modifies the current to get the same effect as connecting external delta CTs as delta or Y, which we will explain in the next few slides. And then they have matrices associated with each number 0 to 12 corresponding to the vector group. So now the relay current is a number value K, which is a matrix. K is a number here, and then you have a matrix based on your designation of the winding 1, 2, or 5, or 7, or 11. Based on this matrix changes, and this is your CT secondary current. So CT secondary current is modified with this magnitude and also with the matrix to get the relay current that is used for differential protection. Suppose if it is 0, then K is 1. So essentially the relay is seeing the same current as the CT current. So here IAR is same as A phase CT current, IBR is same as B phase CT current, and ICR relay current C phase is same as the CT secondary current. Now if I select 1, in the case of a delta, what happens is IA minus IB. So it is essentially giving relay current is IA minus IB. So if the low side winding is lagging the high side winding by 30, that is dy, the Y side, we had connected CTs in delta. Essentially by selecting a vector group of 1, you are doing the same thing, and the magnitude is adjusted by this magnitude correction factor K. Now this is a special one, which is 12, where it is taking 2IA minus IB minus IC as the A phase relay current. So we'll show in the next slide that how this comes down to be same as A phase current without the zero sequence inside that. There is IA minus I0. Okay. So now if compensation of 0 is this, as I explained, and 1 will give you IA minus IB divided by square root of 3. And then if you use 12, it is 2IA minus IB minus IC. Minus IB minus IC is same as IA, so it is minus I0. So it is 3IA minus 3I0, sorry. It's not I0, 3I0. That divided by 3 gives you IA minus I0. You're taking away the zero sequence component. Why is this required? Because in a Wye transformer, the zero sequence currents are not the same on both sides. You want to use a delta connected CT. We could have used either compensation setting of 1, or if you use the same Y connections, then you have to remove the zero sequence using this. So this table essentially tells us how what settings, compensation settings that can be used in the microprocessor based relay. Y delta, if CTs are connected in Y, then your 11 or 12 can be used. We cannot use 0, and then because there will be only zero sequence current on the Y side with the Y connected CT, and then there is no zero sequence current on the delta side, it will misoperate. So you have to remove the 0 sequence for measuring purposes. So 11 or 12, and then or 0 or 1, depending on, because 11 and 0, 0 is lagging 11 by 30 degrees, or 1 is lagging 12 by 30 degrees. So that is what we use. Okay. And then similarly, delta y, we are using 0 and 1 because delta side is y, and y side we are using 1. That gives us as IA minus IB, as we did in electromechanical relays. You can go back and look at it. Auto transformers, typically 12 or 1 or 12 or 1 don't use 0. Wye transformers, 12 or 1, same thing. Um, uh, these are pretty much the same, and it has been given twice here. And then you have YY with delta tertiary. Then you are using 1 for tertiary because it is a delta. Then it is lagging the Y side by 30 degrees. So we are using this 30, and we are taking away the 0 sequence components on the Y side. Okay. Effectively relay compensation, essentially what it is doing, it is effectively calculating um, uh, calculates the currents as if external CTs are connected in Y or delta. That is what the basic intent is, to take care of the phase sequence of the relays. If you want, let's look at some of the examples of how to set an electromechanical relay and how to set a microprocessor based relay. So we take a simple 115 kV to 138 kV 70 MVA transformer. We go through this. So electromechanical relays, I have selected General Electric BDD relay, and then most of those electromechanical relays pretty much follow the same. And then it has a ratio correction taps, matching taps of 2.9 to 8.7. This is to take care of not using the auxiliary CT if the ratios are not, CT ratios are not exactly selected from high side to low side. And then the main CT connections are, CTs are definitely connected as to compensate for the phase angle shift. Electromechanical relays did not have this facility to change the phase angle relationship. So we have to connect them in delta or Y to account for the phase shifts. So 70 MVA transformers, delta Y, we connected CTs on the high side in Y and low side in delta, and these are the relationship between the currents. So let's look at it. It's a 118 kV on the high side. It's a 70 MVA. So winding is connected in delta. The full load current is nothing but kVA divided by square root of 3 times kV, 3-phase kVA. That is 1000 MVA. Or you can connect as a single phase MVA is 70 divided by 3. And then if you divide it by square root phase to ground voltage, I get the current, which is 342.5. And then you convert the find out full load current on the low side, which is 2929. So you select a CT which is normally can handle current. Normal current is more than your full load current. So as 400 to 5 CT is used here, 3000 to 5 is used on the low side. If you take the ratio, the secondary current when the transformer is fully loaded is 4.28 amps, whereas it is 4.88 amps on the low side. CTs are connected in Y on the delta side in electromechanical relay. So the relay also will see 4.28 amperes. But on the low side, the CTs are connected in delta. The relay current is by square root of 3 times 4.88. It is seeing 8.45 amperes. So the ratio of the two currents is now 1.1 to almost 2, 1 to 2. 197.97. They have a 2 to 1 ratio. Now we have this relay has got a ratio tap. So you select the ratios in such a way of the taps in such a way on those sides so that the tap to the ratio of the currents is same as the ratio of the taps. If you do this, ratio of the currents of 1 to 1.974, here you get 1 to 1.93 by connecting, selecting a tap of 4.5 for this winding and 8.7 for the low side winding. The error is at about 2.77%, minus 2. If you select 4.2 here, the error is nearly about 5%. So 4.5 gives a better less errors in measurement. So it is used. So settings selected is 4.5 and 8.7. You go through the manual on the website of General Electric, and then please spend some time to understand how it is done. It gives you a good concept. Though we may not use electromechanical relays, it gives you a very good insight of how there's relay philosophies were developed. Relay parameters now, if you look at it, it's 4.5 and 8.7. These are the tap settings. And then relay minimum pickup is not selectable in the relay. It is designed in such a way that it is about 30% of the tap ratio. So the minimum current for the relay to operate, if there is only current on the high side, is 1.35 amps, which is 30%, 4.5. And low voltage side is about 30% of 8.7, which is 2.61. Slope, this relay provided us three slope settings: 15% or 25% or 40%. So based on this, you can use. Again, you have to make sure that the relay uses minimum of the two currents for slope setting. If it is zero, it is not using that, but it is looking at the current coming into the relay and current going out of the relay. BDD uses minimum of the two currents to take that as a restraining current. And then that restraining current percentage multiplied by this percentage is the minimum operating current. It could be 15, 25, or 40. You select higher slope if you are not sure about the CT performances, and then you can use 25% or lower if you see that your accuracy is pretty good on the CTs. Harmonic content is also fixed in the relay, which is 20% of the second harmonics. If relay blocks, if the second harmonic content exceeds 20% of the fundamental in the operating current. And there is a high set value. If the current is extremely high, 8 times the tap, the relay knows that it is not an inrush. There must be a fault. Then it doesn't even calculate the harmonic restraint. If the current exceeds that 8 times the full load value, it operates without even checking for the restraint, percentage restraint. So in short, we can just summarize this as the relay taps or CT connections current and relay current is this. So we selected it. Sorry, this is about CT relays without the CT ratio adjusting taps. Then what we found is the CT currents are 4.28 and 8.45 on the secondary side. I have to select an auxiliary CT here so that I can make the current, the restraining currents on both sides pretty close to each other. The error is 1.3, assuming 2 to 1. How we do this? We go back and put an aux CT on this side, on the low side, so that the current here is 8.4 and here it is half of that value. So essentially, you connect an auxiliary CT. This is a situation where you don't have ratio adjusting taps in the electromechanical relay. So these are all conventional relays. The reason why we covered it is most of the relays may still be electromechanical in the system, though we are in the microprocessor world now. And then you may have to work on it in some cases on legacy systems. So it is good to know how these operate. Microprocessor based relays, on the other hand, it gives you all the flexibility for phase shift or ratio adjustments, and then you can select the minimum pickup, slope, and harmonic restraint and high set, which most of them were pretty much not available in electromechanical world. So we'll go through the same calculations here. 70 MVA windings are connected in delta and Y here. And then vector group is 0 and 1. This is shifted here. It is actually delta on the high voltage and Y on the low voltage. Some relays don't even need this. They automatically take care of this by not using the zero sequence current. And then you know that the low voltage side lacks high voltage. That's why we selected vector group of 1 on the low side. Same CT ratios are used. We calculated the currents here, and then the relay takes this current as 100% or 1 per unit current in determining how it should operate based on the settings which we provide. So minimum pickup, if I say it is 0.3, it takes 0.3 times 4.28 as the minimum current required for the relay to operate if the current is flowing only on the high side, which is 1.28 amps, or if you have current is only flowing on the low side, then it is 1.464 on the low voltage side. Relay also removes errors due to zero sequence currents. Slope settings can be set from 0 to 100, whereas in electromechanical relays we had 15, 25, or 40 in our example. Second harmonic and additional harmonic restraints can be set. You can select any numbers. In the electromechanical relay, it was set to 20% in BDD. Here we select either 15 for second and then 15 for fourth. You can select different harmonics for operations. And then percentage of harmonics to prevent relay operation, you can use the numbers. Now here I said harmonic can be second and fourth, and additional harmonics are available, and you can select the percentage